As the sun dips below the horizon, its light begins to fade. Night falls and our world descends into darkness. Today, in our street-lit towns and cities, we rarely experience true darkness. But without our eyes to guide us, the world becomes a much more mysterious place. I can't see anything now, but strangely, I can still sense the presence of the trees enveloping me in the gloom. I can't see them, but I know there's something out there. And in the same way, as we've explored the cosmos, we've come to realize we can only see the merest hint of what's out there. Our best estimate is that more than 99% of the universe lies hidden in the dark, invisible to our telescopes and beyond our comprehension. This film is the story of how we went from thinking we were close to a complete understanding of the universe to realizing we'd seen almost none of it, and the extraordinary quest to uncover what's really out there in the dark. It's perhaps the most important undertaking in science, because our universe was forged in darkness, and darkness will one day tear it apart. For centuries, scientists have used light to build up a seemingly comprehensive picture of the universe. We discovered that the Earth was just one planet in orbit around the Sun, and that the Sun was itself a star made of the same stuff as the billions upon billions of stars that light up a vast, perhaps endless cosmos. But there was one niggling problem that had remained unsolved for over 400 years, and it was this. With so many stars out there, why was there any darkness at all? The story of the dark begins with this simple question. And at its heart lies a deep paradox. In the forest, no matter what direction I point my torch, the beam will always hit the trunk of a tree. And just as everywhere I look I see a tree, if the universe is sufficiently large, then every line of sight from Earth should end in a star. The night sky shouldn't be black at all. It should be ablaze with starlight. First posed in the 1570s, this question would become known as Olbers' paradox. One possible solution was that the Earth was surrounded by dark stuff that obscured our view of the stars behind. But it was soon realized that these dark clouds would absorb the light from the stars, heat up, and eventually glow with the same brightness as the stars they obscured. The paradox was only satisfactorily explained in the 20th century. The answer, the reason it gets dark at night, is because the universe had a beginning. It began with the Big Bang 13.8 billion years ago, and so we only see those stars whose light has had time to reach us since then. The sky is dark because light from the most distant stars hasn't got here yet. No mysterious stuff was needed to block out the light. The dark spaces that starlight had yet to reach were empty, and cosmologists could sleep easy at night. But before long, we began to see hints that there might be more out there than meets the eye, that the shadowy recesses of empty space might not be so empty after all. The first clues had in fact begun to emerge from the gloom some 200 years ago. Not in the depths of the universe, but in our own backyard. The invention of the telescope in the 17th century had allowed us to see the dimmest light from the deepest reaches of the solar system. And in 1781, it had revealed a seventh planet, Uranus, the first to be found since ancient times. But there was something odd about this new planet. Astronomers had found that as time passed, Uranus's actual position was drifting further and further away from the position the laws of gravity predicted it should be at. Now, one explanation was that the laws themselves were wrong. But working at the Paris Observatory, one man came up with a different solution. There was something else out there, something we couldn't see that was interfering with Uranus's orbit. In 1846, the mathematician Urbain Le Verrier was employed at the observatory to calculate the orbits of comets as they wandered through the solar system and predict when they would light up the night sky. Le Verrier has been described as having an almost pathological need to impose order on everything and everyone around him, and to have made no allowances for human error or frailty. When asked what he was like, a colleague remarked, "I do not know whether Monsieur Le Verrier is actually the most detestable man in France, but I am quite certain that he's the most detested." But he was undoubtedly a mathematical genius, and he was as harsh on himself as he was on others. And because he was a mathematician, he set about finding the object he thought was influencing Uranus, not by scouring the skies with a telescope, but by determining its position through calculation. These are Le Verrier's original handwritten notes from 1846. This one's called Searches of the Disturbing Body, Second Approximation. It contains page after page of complicated mathematical calculations. What Le Verrier was attempting was quite different to what was normally done in astronomy, where you know where an object is, say a star or planet or comet. You then use the laws of gravity to explain its effect on nearby objects. Here, he didn't know where his disturbing body was. All he had to go by was the effect it had on the orbit of Uranus. So he made some starting assumptions about its position, and then carried out a calculation to predict the effect it would have on Uranus. He then compared that with what had been observed. When the two didn't match, he went back and adjusted his starting assumptions and repeated the calculation. He did this again and again until his prediction matched the observation. On the 31st of August, 1846, after 3 months of painstaking work, Le Verrier presented his results to the French Academy. He announced that his calculations had revealed what he believed was a new planet. and crucially, that he had the coordinates in the night sky that showed where it could be found. And yet, despite this, he was unable to persuade any French astronomers to search for his planet. Eventually, Leverrier sent his calculations to Johann Galle at the Berlin Observatory. His letter arrived on the 23rd of September, and the new planet was found the same evening, within 1 degree of Leverrier's predicted location. His calculations were so precise, it took Galle less than an hour to find it. Leverrier and Galle had discovered the planet Neptune, a vast ice giant, 17 times heavier than the Earth and nearly 60 times its volume, lurking in the shadows some 4 billion kilometers from the Sun. Neptune had been hard to find not because there was anything inherently mysterious about it. It's dark simply because it's so far from the Sun, there's precious little light to illuminate it. And outside our solar system, this lack of illumination is an even bigger problem. And it means even more stuff is hidden in the dark. Stars are thought to contain just 11% of the atoms in the universe. The rest, clouds of gas and dust, planets, dead stars, we can't see because they give off hardly any light. The dark spaces between the stars aren't empty at all. In fact, they contain the vast majority of the stuff that's out there. Up until the middle of the 20th century, most astronomers believed that although they couldn't see nearly 90% of it, the universe was still, theoretically at least, entirely visible. But that was about to change.
Welcome to White Sands Missile Range.
In 1964, NASA scientists fitted an Aerobee rocket with an X-ray detector and blasted it to the edge of space. High above the X-ray absorbing layers of the atmosphere, the detector spotted something extremely bright in the constellation of Cygnus. The young British astronomer Paul Murden was fascinated by this mysterious X-ray source known as Cygnus X1. And when he joined the Royal Greenwich Observatory in the summer of 1971, he was given the perfect opportunity to discover what it was. It was known that X-rays were produced when gas was heated to temperatures upwards of 1 million degrees. Hello, Paul. But no one knew for sure what could produce such extreme conditions out in space. What was it about X-ray sources that interested you?
The celestial X-ray sources had just been discovered. They were places in the sky where X-rays came from. It's a very energetic radiation. It means something really powerful is happening there. And the X-rays are a flag which the star is waving at you, saying, look at me, look at me, look at me, I'm really interesting.
But when Paul trained his optical telescope on the source, all he saw was an ordinary, everyday star, nowhere near hot enough to produce X-rays.
Most stars are in systems where there's 2 stars, 3 stars, even 5 stars, or many more. It's really unusual to have a star like our Sun that's on its own. I decided, therefore, that I'd try and look for evidence on the star that I could see that there was another star nearby and that they were circling one another.
By recording its motion night after night, Paul discovered the star was orbiting an invisible partner once every 5.6 days.
What you can calculate once you know the period of a binary star is the mass of the system and the mass of the component parts of it. And so that was the thing to do next. And then maybe within an hour, I knew that the star which I couldn't see was 4 solar masses or more.
Something that heavy, so close to the star he could see, would strip material from its outer layers. The immense frictional forces heating the gas to such an extent it produced X-rays. But physicists only knew of one object that could be that massive and yet remain completely invisible. It was something that had only ever existed in theory. Paul Murden had discovered the first black hole.
I was just elated. And I had to get up from my desk and walk about a bit to calm down. My pulse raced. I knew it was big, but I was also a little bit frightened of it, so I knew I had to check it very carefully and go through it all again and check what I was doing. But it was a great hour, and I couldn't really do any serious work for the rest of the day. And I felt really happy with myself, actually.
Thanks to Paul Murden, the universe now had a new and profoundly dark inhabitant. Black holes are so incredibly dense, their gravity warps the fabric of space and time around them to such an extent that nothing, not even light, can escape.
As you approach a black hole, an observer watching you from a distance will see the light coming from you getting redder and redder, and you will appear to be moving in slow motion as the immense gravitational field of the black hole stretches both space and time. And then, as you pass through the event horizon, the point of no return that marks the edge of a black hole, you simply disappear, lost from the universe forever.
Black holes are objects that would remain dark no matter how much light you shone on them.
Through their effects on other things, we've now discovered dozens of black holes in our own galaxy, and estimate there must be billions upon billions of them throughout the universe, including huge, supermassive black holes, millions of times the mass of the Sun, at the heart of nearly every galaxy.
As strange as black holes are, they were at least something we'd expected to find. We had theories that predicted their existence and described their properties. But since the 1930s, astronomers had seen disturbing hints of something much stranger. Stuff that was both completely invisible and completely unexpected. As a child, Vera Rubin spent hours awake at night staring out of the window above her bed, gazing at the stars as they moved across the sky. Then, in her 30s and a mother herself, she decided to realize her childhood dream and embark on a career as an astronomer.
In the mid-1960s, the hottest topic in astronomy was quasars. But the field was extremely crowded, and because the biggest telescopes that were needed to study them were often in the remotest parts of the world, working on quasars meant a lot of time spent away from home. So Vera needed to find a research topic that was more compatible with being a working mum. and a smaller field where she could really make her mark.
So she began a project measuring the way stars move within galaxies, like our own Milky Way.
Everything in a galaxy is on the move and rotating. In 1 minute, the Earth travels nearly 2,000 kilometers around the Sun. But in that same time, the Sun and the entire solar system travel 12,000 kilometers around the center of the Milky Way galaxy. Am I not liking this? If you think this is spinning fast, think about this. The Earth is traveling around the Sun at 108,000 kilometers an hour. And the Sun and the entire solar system are traveling at 720,000 kilometers an hour around the center of the galaxy. Can we stop it now? Yeah, that's done me in, that really has. Thanks very much.
But when Vera Rubin measured the speed of stars orbiting the center of the Andromeda galaxy, she found something deeply puzzling.
If I plot a graph of the speed at which planets in our solar system orbit the Sun against their distance from the Sun, I find that the closest planet, Mercury, orbits the fastest. It's then followed by Venus, Earth, Mars, and so on. The further out you go, the slower the orbit. In fact, Neptune moves so slowly relative to the other planets and has so far to go in orbit around the Sun that it's only completed one full circuit since it was discovered 167 years ago. Now, if I plot the same graph again of speed against distance, but this time, the speed at which the stars orbit the center of a galaxy against their distance from the center, I'd expect to see for the outer stars that the speed drops off with distance as it did for the planets. But when Vera Rubin plotted her data, she found that the further out you went, the speed of the stars didn't drop off. It remained roughly the same. The planets move more slowly the further out they are, because the further you go, the weaker the Sun's gravitational field becomes. So anything moving too fast would simply fly off into outer space. But Vera Rubin's result for galaxies suggested there must be an extra source of gravity holding all those fast-moving stars in their orbits.
This extra gravity was needed because when astronomers added up the gravitational pull of all the dark things they thought might be lurking in the galaxy, planets, clouds of dust, even black holes, it always came out about 10 times less than that needed to account for the stellar speeds Vera Rubin had measured.
There were two possible explanations. Either Einstein's theory of gravity was wrong, or galaxies were full of a completely new kind of stuff. Something that wasn't made of atoms, was completely invisible and very heavy. A new form of dark matter, something astronomers named dark matter.
Unsurprisingly, rather than accept that galaxies were full of some mysterious, unseen stuff, some physicists once again thought tweaking the laws of gravity might be the simplest solution. That was until astronomers captured an astonishing image.
For me, this is one of the most amazing pictures in modern astronomy. It's an image of a cluster of galaxies called the Bullet Cluster. It gets its name from this bullet-shaped cloud of gas here, which is actually a shock wave caused by the collision not of just clouds of gas or stars or even whole galaxies, but clusters of galaxies coming together and passing through each other at 10 million kilometers an hour. It almost gives me vertigo trying to imagine the immensity of the scale.
But it's not the magnitude of the collision that makes this image so important. It's what it did to the cluster's constituent parts.
As the clusters came together, the stars and planets in the galaxies pretty much pass through each other because although they're big, the distances between them are so vast that the chances of any two stars colliding is actually very small. But that doesn't apply to the dust and gas that makes up 90% by mass of all the stuff we can see in a galaxy. When these collide, they create a huge hot cloud, these two pink regions in the center of the image. But if most of the mass is trapped here in the clouds, then you'd expect most of the gravity to be centered there too. But that's not what you see. These outer blue regions show where light has been bent round as gravity warps the fabric of space itself. That means most of the gravity is centered out here rather than in the middle. The simplest way to explain this is that it wasn't just the stars and planets that passed through as the clusters collided, something else did too, something massive yet invisible. This image is the best evidence we have yet for the existence of dark matter.
It's now generally accepted that dark matter is real, which means there's far more stuff in the universe than we'd thought. In fact, there's 4 times as much dark matter as there is normal matter. And so vast swathes of the universe are not just unseen, they're fundamentally unseeable.
The reason dark matter is so elusive is because it doesn't reflect light and it doesn't emit light, so we can't see it. And worse than that, what gives normal matter its solidity is the electromagnetic force. And dark matter particles don't feel that force, so they just pass straight through matter. The only hope we have is if they hit an atomic nucleus head-on. And even if they do, that's really hard to detect.
And so the hunt for dark matter has turned from the incredibly large to the unimaginably small. From scouring the skies with telescopes to detectors buried deep underground.
When it comes to the search for dark matter, the place I'm going to is pretty much the center of the universe.
The Gran Sasso National Laboratory lies beneath almost 1.5 kilometers of solid rock and can only be reached through a tunnel cut deep into the Italian Apennines.
The reason you'd build a laboratory underneath a mountain is because our planet is constantly being bombarded by cosmic rays. These collide with the upper atmosphere, creating a cascade of particles that shower down onto the surface of the Earth. The rock above me effectively forms a 1,400-meter thick roof that absorbs most of these particles, shielding and protecting the equipment below. But crucially for dark matter hunters, it passes straight through normal matter, straight through the rock, and the hope is into their detectors. looks like a Bond villain's evil lair.
Gran Sasso is the world's largest underground laboratory. And for the last 10 years, it's been home to dark matter scientists like Dr. Chamkur Garg, who works on Dark Side 50, one of 5 dark matter experiments based here.
So hairnet, or headnet in my case. Milligram levels of dust can destroy the experiment. Right.
That looks very impressive.
Yeah, very sci-fi.
So tell me, how does the experiment work?
Well, the entire experiment is configured like a Russian doll, where the first outer layer is the mountain itself, protecting the experiment from radiation from space. Then we have this tank that we're standing in, and this tank itself is going to be flooded full of water.
What, the whole cylinder?
Absolutely, yep. This is all completely filled to the brim. About 750 cubic meters of water will fill this thing to stop radiation coming from the laboratory and the rock around us. That's protecting this huge metal sphere right here, which is the final layer of protection before we get to dark side itself, which is inside there right now.
So that's the detector, that's the heart of the experiment.
That's right, that's the thing that will be detecting dark matter.
So I guess there's no, you haven't got a light switch up there, so I'm going to get up there and have a look.
Dark Side 50 is designed to detect a new class of fundamental particles called weakly interacting massive particles. Predicted by theory, it's thought that these WIMPs might be the stuff of which dark matter is made.
So that metal sphere in the center, that's dark side.
That's right, that's a detector that's full of 150 kilograms of liquid argon. Dark matter particles should be streaming through the detector all the time, but most of them just go straight through because they're very weakly interacting particles. But if we're lucky, one of them will collide with the nucleus of an argon atom, producing flashes of light that the detector will pick up.
Dark Side is yet to begin its search, but elsewhere in the laboratory's labyrinth of tunnels, they're already seeing tantalizing hints.
This is the Xenon 100 experiment that's actually already running and taking data and has been for a while. It's actually the most sensitive dark matter detector in the world right now. And this is a live feed of dark matter data coming in right now.
So what sort of signal shape are you looking for?
Well, what we're looking for is an initial flash of light, which will be a very sharp peak like this, followed by a much larger peak like that one, which is light being generated in a gas layer on top of the liquid xenon. Oh, that could be a good one as well, actually. There you go.
So any one of those events, those spikes, could be a dark matter particle?
That's right. Any one of these events could be the signature of dark matter interacting in Xenon 100. It's just that we won't know for sure until the data's been analysed.
Because it's so sensitive, the overwhelming majority of the spikes are due to radiation emitted by the metal that makes up the detector itself. But the hope is experiments like this will definitively detect dark matter particles within the next 10 years. Today we think that dark matter not only exists, but that it is a vital part of our universe.
because without it, the world that we can see wouldn't exist. And that's because dark matter not only holds galaxies together, it's dark matter that brought the clouds of gas together to form the galaxies in which stars could ignite in the first place.
Dark matter has gone from being a curious quirk of the way stars move around the fringes of galaxies to the reason there are stars and galaxies at all. But in the late 1990s, scientists attempting to measure exactly how much dark matter there was made an astonishing discovery. There was something even more mysterious and even more elusive out there. And to understand what that is, you have to go back to the very beginning of everything.
The universe began with a gigantic fireball.
13.8 billion years ago, the universe was born.
In the so-called Big Bang, everything was created simultaneously.
See that great flash of light? That's all the pieces of the atoms joining together to make a gas. And now the gas is getting lumpy. It's making the giant galaxies of stars.
The expansion of the universe that we now see is just a remnant of the initial violent explosion.
The Big Bang means that in the past, the universe was much smaller than it is today. And it's been getting bigger ever since.
According to the Big Bang Theory, the universe has been expanding for the past 13.8 billion years. And for most of that time, you'd expect the expansion to be slowing down due to the combined gravitational attraction of all the mass in the universe trying to pull it back together again. Now, here's the clever bit. Cosmologists realized that by measuring how much the expansion was slowing, they could calculate how much stuff was out there. In a sense, it would allow them to weigh the entire universe.
But in order to measure how the universe is expanding, you need a reliable way to measure distances in space. Something of known brightness astronomers call a standard candle.
The flame in this lantern produces a fixed amount of light. It has a specific brightness that I can measure here on the ground. But if I let the lantern go, it'll drift away and the light will appear to get dimmer and dimmer the further away it gets. Because I know how bright it really is, by comparing that with how bright it appears, I can calculate how far away it is. And because every lantern's the same, I can use the brightness to calculate the distance to any lantern I see in the sky.
The astronomical equivalent of a Chinese lantern is a particular species of exploding star called a Type 1a supernova. These stars always explode when they reach the same critical mass, and so always explode with the same brightness. So by measuring how bright they appear, we can tell how far they are from the Earth.
As well as telling us how far away they are, the light reaching us from distant supernovae tells us something else. As it travels across the cosmos, light gets stretched because the space it's traveling through is expanding. And as its wavelength increases, the light gets redder and redder. And this redshift tells us how fast the universe was expanding when the light left its source, when the star exploded. But when scientists analysed light from the more distant supernovae, they found something strange. It was less stretched than expected. It meant that in the past, the universe was expanding more slowly than it is today. In other words, the expansion of the universe wasn't slowing down at all. It was speeding up. The only way the universe's expansion could be accelerating was if there was a mysterious new force pushing it apart. And just as with dark matter, physicists thought the key to understanding this new force might lie at the smallest possible scales. Because quantum physics appeared to provide a ready-made explanation.
According to quantum field theory, empty space is anything but empty. Particles are constantly appearing and disappearing, created out of energy borrowed from the vacuum itself.
The hope was that this theoretical vacuum energy might be the very thing that was pushing the universe apart.
And the theory allows me to calculate the energy density of the vacuum. That's the amount of energy you'd expect to find in a given volume. And so if I take the energy of the vacuum to be a sum over J of half h bar omega J, and if I take the cutoff energy to be of the order of 10 tera electron volts, which is just above the known physics at Large Hadron Collider, then the formula for the vacuum...
All they needed to do was check the energy density the theory predicted.
For the energy density of the vacuum of 10 to the 35 kilograms per cubic meter. The trouble is, the value observed by astronomers is 10 to the minus 27 kilograms per cubic meter. That means the theoretical number and the experimental number are out by a factor of 10 to the power 62. That's 1 followed by 62 zeros. To give you a sense of the scale of the error, there have been only 10 to the 17 seconds since the Big Bang, and the diameter of the entire visible universe is 10 to the 27 meters. So it's a pretty big error.
And that meant that whatever was actually pushing the universe apart, it was something completely new.
The truth is, we know very little about what's causing the expansion of the universe to accelerate, but we do have a name for it: dark energy. And we know that for it to have the effect that it does, there must be an awful lot of it about.
Einstein's famous equation, E equals mc squared, says that energy and matter are different forms of the same thing. And the equivalent mass of dark energy dwarfs that of everything else in the universe. And it means that today, normal matter makes up just 4% of the cosmos. 23% of it is elusive dark matter. And a colossal 73% of the universe consists of mysterious dark energy.
Just think about it for a moment. 100 billion galaxies, each one containing more than 100 billion stars, home in turn to billions upon billions of planets and moons. All of that is mere flotsam, adrift on a vast and unfathomable ocean. Dark matter we can't see, and dark energy we can barely comprehend.
And the very nature of dark energy means the universe is getting more unknowable all the time.
As space expands and distances become bigger, most forces get weaker because you have the same amount of mass or electric charge, only now everything's further apart. But dark energy behaves completely differently. As the universe has expanded, the stronger it's become. The more space there is, the more dark energy there is, and so the faster the universe expands, creating ever more space and ever more dark energy.
And that has a profound consequence. Just as dark matter pulled the galaxies together to create the cosmos as we know it, so dark energy will tear the universe apart.
In the future, as space gets bigger, dark energy will become ever more dominant, and so it will ultimately shape the universe's destiny. And if it continues to increase, as it appears to be doing today, then it will push the galaxies further and further apart until eventually they slip out of view, creating a cosmos that will become ever more dark and ever more desolate.
The ultimate goal of modern cosmology is to understand dark energy and the fate of the universe, and to witness how dark matter brought everything together in the first place. And so to shed light on both the beginning and end of the universe, cosmologists have embarked on a quest of epic proportions to map everywhere in space over the entire lifespan of the cosmos, starting with the darkest period in its past, an era that began as the afterglow of the Big Bang faded away.
We talk about the ages of the universe in the same way that we talk about the stages in our own lives, from its birth through childhood, adolescence, adulthood, and even death. And so mapping the universe is really about filling in the photo album of its life. Here's a picture of me from 20 years ago with my children. I know because I have a lot more hair there. And here's a picture of me in my early 20s on graduation. And here's one of me as a teenager. In the same way, by looking out into space, we have good images of the universe all the way back to its teenage years, when large galaxies first formed. But before that, we have nothing but a single image. A picture of the universe when it was just 400,000 years old, the cosmic microwave background, the afterglow of the Big Bang. It's as though in the photo album of my life, I have nothing before this picture of me age 16, apart from this one of me with my parents in Iraq when I was just a few months old. This gap in the childhood of the universe, the period between its earliest moments through the birth of the first stars to the formation of large galaxies, is a time known as the Dark Ages of the universe.
The universe's dark ages lasted for around 1 billion years, and they get their name because there were precious few stars to illuminate them. So to fill in those pages in the cosmic photo album, we'd need something capable of seeing where there was next to no light. During the Second World War, Bernard Lovell had developed a machine that could see in the dark. He'd worked on airborne radar that mapped bombers' targets on the ground. But his real ambition was to build something capable of mapping the heavens.
The giant dish at Jodrell Bank was Bernard Lovell's baby. It was designed to be the world's largest fully manoeuvrable radio telescope, capable of scouring the entire sky and picking up the longest wavelength radio signals coming from the deepest recesses of space.
The Lovell telescope has a collecting area of 4,560 square meters, made up of more than 2,400 galvanized steel plates.
In the original designs, this bowl of the telescope wasn't meant to be solid like this. The plan was for it to be built of much lighter wire mesh.
The dish was redesigned because astronomers had discovered a new way of seeing in the dark, something that might ultimately allow them to map the universe's dark ages.
Hydrogen permeates every galaxy. It was produced in the Big Bang and is the basic constituent of all normal matter, including us. And like most normal matter, it wasn't thought to give off any light. But then astronomers discovered something remarkable. As it floats around in space, neutral hydrogen gas is constantly producing radio waves. And crucially, those waves are always of the same wavelength, 21 centimeters. And this meant that hydrogen could be used to map the galaxies that it fills.
By detecting the 21 centimeter signal, the Lovell telescope helped reveal the spiral structure of the Milky Way and produced detailed maps of distant galaxies.
But galaxies aren't the only place in the cosmos you find hydrogen gas. During the dark ages of the universe, there were no galaxies, but there was plenty of hydrogen. So by detecting the 21 centimeter signal from these primordial gas clouds, you could see the universe in its infancy and peer into the dark ages themselves.
And by doing so, we'll be able to watch dark matter pull the cosmos together and light up the heavens.
It was during the Dark Ages that the hydrogen gas created in the Big Bang was compressed into stars and molded into galaxies. It was in this era that the cosmos as we know it was born, sculpted by the gravitational pull of dark matter.
But the machine scientists are building to map the Dark Ages will see far more. With an effective collecting area of more than 200 times that of the Lovell telescope, the square kilometre array will be capable of mapping 1 billion galaxies, tracking the expansion and evolution of the entire universe more accurately than ever before. And the hope is that by doing so, it'll provide clues to the nature of dark energy and the universe's ultimate fate. Using hydrogen to map the cosmos might just represent the final chapter of humankind's exploration of the universe using light, a journey that began in earnest some 400 years ago.
In December 1609, Galileo Galilei began making observations of the night sky. Before then, what was thought to be out there was essentially a matter of faith. The universe at large lay unseen and unseeable. But now, for the first time, the nature of the heavens was something knowable. You simply had to look up and see it. The light captured in Galileo's simple telescope began a chain of discoveries that would reveal the true nature of the cosmos.
We've seen galaxies billions of light years distant from the Earth. And as we've come to understand light's properties, we've discovered the stuff of which stars are made, and glimpsed the beginning of the universe itself. But the realization that most normal matter can't be seen, and the discovery of dark matter and dark energy, mean that more than 99% of the universe lies hidden in the shadows. And as dark energy pushes the galaxies ever further apart, what few lights there are will begin to go out.
As the universe expands ever faster, one by one, the galaxies will disappear from view. All that will remain visible will be the stars in our own galaxy. It will be almost as if we'd never invented the telescope at all. For the vast majority of the universe's life, there'll be no way of discovering all the things we have about it. So I don't feel disheartened that so much of the cosmos is hidden in the shadows. The real miracle is that when we first looked out into the depths of space, there was any light to see at all. Whether you want to step into the light or explore the mysteries of the dark, let the Open University inspire you. Go to bbc.co.uk/light and dark and follow the links to the Open University.
Secret Knowledge profiles one of the most celebrated artists of the last century here on BBC4 this evening. Tracy Emin on her friend and collaborator Louise Bourgeois in just a moment.
As the sun dips below the horizon, its light begins to fade. Night falls and our world descends into darkness.